Great. Can everybody hear me right? Okay. So, hi everyone. My name is Ethan Jimenez from Microsoft Edge layout team, and I'm here today to share with you some of the insights from the CSS Subgrid implementation and the many challenges that we face during its development. We don't have much time, so let's dive right into it, into the rabbit hole of GridNG. We'll start by going over some concepts that will help us understand why Subgrid is so important. And let's take my favorite example with a big shout out to Cambelos and his amazing blog post that I reference all the time for Subgrid. So let's say that we want to display a set of article cards, each one with a couple of counters. In the image here, we have like a like counter, a unicorn counter, and a bookmark counter. The important bit of this example is that we want those counters to be aligned to each other, like the grid lines represent here. The pink line, sorry. There's a couple of ways that we can approach this behavior, and the first one is using floats. But the big problem with floaters is that the counters will stick to the left side, and we don't really have them aligned to each other. We could set the main container as a grid and then use display contents on the article cards, which will introspect the grid items, or well, the children of each of the article cards to the parent. And that way, we have the counters aligned, but then we don't really have the nice border box of the article cards. That's the problem with this approach. And we can also use JavaScript to place the contents of the cards and use a backdrop that we can manually place so that we can adjust it with a Z index, but that will be a lot of trouble to do. So fortunately, we have Subgrid coming to the rescue. And as with the second approach, we want to make the main container a grid and let the article cards be also a grid containers, but we will use a definition on the columns for those article cards, highlighted in blue, to be subgridded, meaning that they will be taken from the main container. With this example, we will start looking at some summary definitions. First of all, we want to know that the axis of a grid container, with a subgrid definition, with the subgrid keyword, is known as a subgrid axis. And just that we mentioned, it means that the tracks or the track sizes of this will be taken from the parent grid. For the rest of the presentation, I will have this like common notion that the lines that are like dotted will be subgrid axis. In this case, they are like template column subgrid, so they are dotted on the column axis. And the other ones, like the straight lines, will be what we know as a standalone axis, which is one axis that it's not subgridded, of course, meaning that it has its own definitions, like an auto repeater, an integer repeater, or any kind of a definition that are for the subgrid alone. And with those, we can finally define a subgrid as a container with at least one subgrid axis. It is important to note that these subgrids are not required to have both subgrid axes. We can have one and one. And of course, a standalone axis is one that it's not a subgrid. So another key definition here is a subgrid item. Any item from a subgrid, for example, the titles that are highlighted in pink or the counters that are highlighted in blue are considered by the parent grid of such subgrids in the subgrid dimensions. In this example, we can see that the lines in there go straight across the subgrid axis and into the parent, meaning that they will be considered by the parent grid. And finally, we have a definition that it's not really in the spec, but it is important to understand to talk about implementation, and it is the definition of a root grid. It is the lowest ancestor of a subgrid that is a standalone grid, meaning that such root grid originated the subgrid chain up until that point. For example, in the figure, we have a subgrid in blue and the root grid in pink. Its immediate parent then generated the subgrid. And in this other one, the subgrid still is being generated by the same root grid. But in this other case, we have a subgrid right in the middle that is originated by the root grid that is the parent above. While this root grid is also nested, since it has both standalone axes, it establishes its own grid independent context. So it will kind of like break the subgrid chain. And moving on, I would like to quote a very famous phrase from Uncle Ben. With weird power comes great implementation challenges, or so I remember from the Spider-Man movie. With that, let's go into the nitty-gritty of why subgrid required very thoughtful consideration for it to implement is starting with placing grid items in a subgrid. From the CSS2 spec, we have the placement of all grid items, included subgrids, and their sub-items occurs before sizing. And this effectively means that the placement algorithm needs to recurse into subgrids and finalize all of their placement before the sizing happens. This was challenging to accomplish because subgrids need to inherit the grid line names of its parent. And the class that does this in GridNG is the ng-grid-line resolver. But before subgrid, it only took into account the line names from the grid's computed style. In this example, we have a standalone definition of a root grid that has 2 intrinsic columns and 1, 2, 3 grid lines that are called ABC in that order. If we have a nested subgrid as this one, when its own line names are defined in X, Y, Z, we expect that the subgrid is aware of both set of line names. So we want the ABC from the parent, but have it accumulated on the next level of subgrid. Like in here, we have for the first one A and X, B and Y, and Z and Z. It is important to remember that the cumulative set of set lines should also be available for out-of-flow items, because this last bit is tricky to accomplish if we want to collect the inherited line names from a subgrid at the time that we place the out-of-flow items, since we would need to go up the tree collecting them instead of like just going up to bottom. The other big issue with subgrid was the placement of, the other big issue with subgrid placement was resolving the auto repeaters. I will go briefly over this example. Let's look at the root grid that is highlighted in pink. Its template columns definition has like 3 intrinsic sizes. And we have a blue subgrid that has a standalone axis with an autofill repeater right in the middle. It has a definition of 50 pixels, meaning that we should repeat a track of 50 pixels up until we fill out the available space in the inline size. Since the root grid tracks are defined as auto at the very beginning of the algorithm, we know that the inline size for the containing block of that subgrid, it's indefinite by definition. So we would resolve the number of repetitions here to 1. But after we consider the pink subgrid item in the bottom that has like 100 pixels width in the sizing algorithm, then the containing block for the subgrid will change. And this will trigger, if we recompute the number of automatic repetitions for that subgrid, we would possibly end up with a different value. In this case, since the containing block changed to 100 pixels, the resolve outer repetitions would change to 2, which could trigger a lot of discrepancies between how we size the rows. Like if you remember in the past slide, we place one item in the only column when we assume that we had just 1 repetition and the other one in the next row. And if we recompute and have 2 different results for the outer repetitions, then we will end up with the 2 of them being in the first row. That can result in some discrepancies on how we sized the items and how we actually laid them out. So that's what we decided, that placement needed to be done entirely by the root grid. And it will be cached so that subgrids can reuse that. We won't recompute grid placement after the root grid's done with the sizing algorithm. This is useful for out-of-flow item placement, since the line resolver will be cached on the grid node, meaning that we don't need to accumulate the line names again going from bottom to top. So here's a brief snippet of how the placement algorithm recurses into subgrids. It's not the actual code that we have in GridNG, but it closely represents the ideas. We call a place grid items for a given grid, and we will pass the inherited grid line names in the parent grid line names variable. And first, we want to create an accumulated line name set where we merge all of the grid line names from the parent and the ones that are computed on your style. Then we will use that to cache the placement of non-subgrid items in the construct grid items method. And then for every subgrid that we encounter in the grid items collection, we will go ahead and recurse into them. So next, let's talk a little bit about challenges of grid sizing, which in my opinion is like the source of all evils in subgrid. So originally, we had a thought of how we could get away by simply creating a set of span tracks for a subgrid and just translate them to the subgrid's writing direction and pass them through the constraint space and let the recursive calls to layout and compute min-max sizes handle the rest of the sizing algorithm. If a grid container had inherited tracks in the constraint space, we will not run track sizing for those, and we will just assume the values that we have from the parent. This sounded like a great idea at first, and it would have been a great idea. But when we have, well, actually, this was a great idea when we have both subgrid access, just like we have in this example. We have a root grid and two subgrids that are completely delegating the job to their parent. In this example, whenever we want to get the inline size contribution of a subgrid item, we would consider the span rows of the item in the root grid delegated twice as easily. And it will happen the same thing for the other axis. The columns of the root grid are the only one used to determine the containing block of any subgrid item in this example. But as many things in life, that seem too good to be true. And let's add a standalone axis into the mix. In this other example, now we have columns of the subgrid being standalone, meaning that we cannot delegate the job of getting the columns to the parent. And when measuring the block size of this subgrid item in the middle, we need to determine the containing block of such item from the columns spanned in the subgrid. This was not trivial because at the point where we are sizing the columns, we are sizing the rows of the root grid, we have not determined the columns of the subgrid. So it was kind of like difficult to know how to retrieve those span tracks in the subgrid. And those, we determined that this was not as easy as we initially thought, and discovered that that was just basically the tip of the iceberg. I will very briefly go over an example that it's much more complicated, and I will not even go through all of the example. Consider that we have like a series of alternating, well, a series of subgrids with alternating standalone rows, subgrid rows, standalone rows, just like in here. In order to complete the track sizing for this root grid, in order to complete the track sizing for the rows of this root grid, we need to consider the block size of the highlighted subgrid, the second highlighted subgrid, right in the middle. But in order to compute the min max sizes of that subgrid, we need to inherit the columns of the parent grid. But in order to compute the columns of the parent grid, we need to consider the inline size of this other subgrid, and so on, and so on, and so on. This way of recursing into subgrids was simply not viable in our initial idea for subgrid. And the original approach was not only very complex technically, it was also like a pain to debug, or at least that's what we imagined it was going to be, like super hard to talk about. Well, this case that we are resolving with subgrid should have these results, but then our algorithm was performing something very different or something very difficult to understand. But fortunately, the spec clarifies a lot with this bit from the, well, grid sizing drills down per axis into subgrids rather than completing both axes into recurses. And that pretty much means that we need to process all of the subgrids at each step of the sizing algorithm sequentially. In this example from before, instead of trying to finish a full run of the sizing algorithm and then going to the next subgrid, we want to perform only the first step. In this case, it will be resolving the columns, and we will want it to complete for the root grid, then for this first grid, then go into the third grid, and so on and so on. Then perform the second step that will be resolving the rows of the root grid, and do the same thing. First, finish it for the root grid, then finish it for the second grid, and so on. What this process describes is our next key feature for subgrid, and similar to how placement for all subgrids is triggered from the root grid, we want the sizing algorithm to be completed for all subgrids at the time that we size the root. As such, we introduce the concept of a grid tree. Well, not really we created the tree, but it's a structure that will not hold. Sorry, it's a structure that will not hold only the sizing data of the root grid, but it will contain the information of all of the subgrids in the tree. And all of the sizing algorithm methods in the grid module were refactored. I'm talking about initialize track sizes, compute use track sizes, computing the alignment baselines, were refactored to consider this grid tree instead of just the set of columns and rows from the root grid. And talking about this ng-grid sizing tree, this is the key structure that holds the columns, rows, and grid items for each of the grid containers in the grid tree. To complete the step of the sizing algorithm, we can send this entire tree and a pointer to where we are at each time. And for example, here we have the root grid highlighted as the pink container on top. And then we can recurse into their subgrids, moving on with the algorithm. We start in the root, then we move into each of the subgrids, performing the same, basically the step of the algorithm. If we found a standalone axis, just as we do in the pink highlighted, we will compute their own columns. And if we found any kind of a subgrid axis, instead of doing that, we will be just copying and translating the resolved sizes from the parent. This behavior is much more predictable, and it's really easy to debug since we have all of the data for the subgrids available at all times. And at the end, since we already computed the sizes of every grid in the tree, we don't want to discard that data. So we want to inherit the finalized sizing information in the constraint space so that the subgrids won't recompute their tracks and they will just perform layout with that information. For this specific purpose, we also have like a very lightweight version of the grid tree that it's called grid layout tree that holds only immutable data, but keeps the same structure as we've seen before. And in conclusion, the grid module was very heavily refactored to handle placement and grid sizing of an entire tree at the same time. It needs to happen right when the root grid is sized and passed down to all of the subgrids. And with all of those refactors completed, we finally overcame the challenges of subgrid. And well, we pretty much know at this point that subgrid has shipped, but I'm very happy to share it again with you guys. We have shipped subgrid since Chromium 1.17. Thank you. And it's now supported in all major browsers. We're just currently failing one WPT that we already have in control and in discussions with the working group to get it fixed. And we have seen little to no major issues at the moment. We highly encourage you to try the module, the new capabilities of Subgrid, and help us file any bugs that you can find. But there's still a lot of work to be done in Subgrid, and we're currently have like a couple of key scenarios that we want to fix before saying that it's completely done. We want to honor the specified width and height properties of a subgrid. We currently have like an issue where the subgrids are assumed to consume the entirety of the space available to them, but this might not be the case. And this is a big issue in interop with most of the browsers, where we can get like the same result for all of them. This is a work in progress. We have a couple of patches to already address this issue, but we still need like a couple more CLs to get in the right place. Very important, of course, we need to investigate performance of the subgrid layout. We did a very good job at landing a lot of big refactors to the grid module without changing a lot of the performance. I think that we pretty much were in a very stable place where we didn't affect at all. But subgrid the scenarios are not being perf tested at all, so we need to introduce some more coverage for that. And finally, we need to fix the depth tools overlay for subgrids. We're seeing some visual glitches when we have mixed writing directions. For example, if we have like a subgrid that is orthogonal to the one of the parent, the grid lines are not going to be very well aligned in the overlay. And we also are not displaying the inherited grid line names. And I would like to give a very special thank you to all of the subgrid task force that have been made this possible. It's been a colossal amount of work, but I think we managed to do it in a very nice and clean way. And thank you very much.
So, do we have any questions? Looks like no.
Nice. Thank you so much.
Oh, never mind.
Oh,
cool. We do have one.
So you touched on performance, and you mentioned that there are opportunities to go faster, which is great. How are we looking in terms of our performance versus other engines in complex scenarios? How do we feel about Subgrid? And are there performance cliffs that developers should be aware of until we get those other issues fixed? Thanks.
That's a very nice question. We currently have, there's even like a very big difference between how Blink performs. Like for example, with Gecko, there's a very neat test case that we always like to quote, but I don't have in hand. That is like the case of a lot of nested grids. This is even not considering Subgrid. Having a lot of nested grids, it's a very important pain point for like Gecko, for example, that Blink just breezes out. We have like these measurements of performance of nested grids that is like, we're pretty much breezing through those tests, and Gecko is struggling with them. It's a very huge bug where it seems like it's hanging. Like so Grid in other browsers, it feels like hanging. I would be surprised that introducing Grid into the mix, it's not really an issue for them, since the base Grid module 1, it's also struggling. So yeah, performance is currently, we're doing pretty much better at that point. I think that probably Ian has like the context of this bug that I'm mentioning.
Yeah, Ian, if you want to go ahead and respond.
Yeah, I think Gecko fixed that performance cliff like late last year or early this year. I forget about when, but still a pretty severe issue in WebKit. Yeah.
Yeah, I've seen the bug demonstrated. It's a very clear, there's an N squared that we're not doing anymore sort of case.
Well, it's actually worse than that. It's exponential complexity. Yeah. So, with like 20 divs or something like that, 20 nested grids, you can get to like minutes long layouts.
They're pretty much doing like a recursion without any caching. So, any other questions? Well, I guess we're good then.
Thank you very much.
Yep.